So enthalpy of reaction. We just talked about the fact that enthalpy is really just like an energy measurement at constant pressure. So the enthalpy change in a chemical reaction, enthalpy change or just the delta H, okay, for a chemical reaction is an extensive property. It means it depends on amount. So if you combust a whole bunch of a hydrocarbon, you're going to get a bigger energy change than if you just combusted a little bit of a hydrocarbon. So that kind of makes sense, okay? The more reactants you use, the larger the change. Now, we can also calculate the energy change for the number of moles of reactants in a reaction. And sometimes you can even have a value. Now, notice we did a combustion reaction. This is propane. We combusted it with oxygen to make CO2 and water, okay? And if we combust 1 mole of propane, it has been calculated that we will get this much energy released. I know it's released because it's a negative. That means it's an exothermic reaction, okay? I can also include that in the writing of the balanced chemical equation. I would say C3H8 plus 5O2 would be 3CO2 plus 4H2O plus, since it's being released, I would write it as part of the products. And I can use this in stoichiometry. Now, if it is being absorbed, instead of writing it as part of the products, I would write it as part of the reactants. Let's look to see how we can use this in calculations, okay? Now, here we have that combustion of propane that we just looked at, okay? It says an LP tank in a home barbecue contains 13.2 kilograms of propane. Calculate the heat associated with the complete combustion of all of the propane in the tank. Okay, well, let's take this a step at a time. Now, they tell us that we've got a delta H value for the reaction of negative 2,044 kilojoules. Delta H is always per mole. Okay, this tells us we have 1 mole that will produce this many kilojoules of heat. So I don't know how much I have, but I have, or how many moles I have, but I know I have 13.2 kilograms. So I'm going to start with the 13.2 kilograms of propane. In 1 kilogram, there's 1,000 grams. And I know from my periodic table that there's 44 grams of C3H8 in 1 mole of C3H8. And based on this value, 1 mole of C3H8 will give me 2,044 kilojoules of energy. So that is going to release 6.13 times 10 to the 5th kilojoules. And that will be negative because that's how much is being released. We can also use that in another type of calorimeter, which we'll be using in lab this week, called a coffee cup calorimeter. Yeah, unfortunately, we're not as exciting as some of the bigger schools. We don't have bomb calorimeters, but we do have coffee cups, thankfully, and we can use those to measure the energy of a reaction. Now, as I said, Q at a constant pressure is equal to our delta H, which is essentially the same as our delta E. So we're still looking at this same thing. Q equals MC delta T. Seen that before? I hope so. So we can use this to figure out how much heat is being given off from a reaction. Okay. What happens is in this coffee cup, we're going to know the mass of water that we put in it, and we're going to know its temperature. Okay. We're going to have the reaction happen in the coffee cup, and we're going to record the change in the temperature. So we'll know the mass of the solution, the specific heat of the solution. Usually most solutions are primarily water. So it's not uncommon to see the specific heat of water used here and the change in temperature. And from that, we can get how much heat is given off for the reaction and then change that to per mole, because remember, delta H is always in kilojoules per mole, and get how much energy is given off from one chemical reaction. So let's take a look at a situation and work through how to do that. So we're going to take magnesium and we're going to put it in hydrochloric acid, because that's always a good time. And that's going to produce hydrogen gas, okay, and magnesium chloride just floating around in solution. We know it's aqueous, so it's, yeah, whatever. Okay. Now, when I look at this, I don't want to get too bogged down, okay? But notice I'm going to be measuring the heat of the solution. What's going on in that coffee cup, okay? Well, what's going on in the coffee cup? Well, I'm going to have 100 milliliters of solution, okay? It is sufficiently concentrated to react the magnesium. Goes up, so we got an exothermic reaction, okay? All right, so we've got 100 milliliters. Do we use milliliters in Q? No, we use grams. But fortunately, they tell us that it's 1 gram per mil. And that makes sense because, again, mostly it's water. We're dropping a little bit of magnesium in there. It's got hydrochloric ions floating around in there. But again, our main ingredient is water. So it makes sense that if we have 100 milliliters, it's still going to be about 100 grams. Okay. They tell us the C to use. And we're going to assume that our coffee cups aren't going to absorb much, if any, in this reaction. Okay. And then we're going to do the change in temperature. So we end up with this is Q, sorry. A Q value of 3009.6 joules. Okay. Well, they want this to be a delta H value, the delta H for the reaction. So this reaction we know produced, based on our 1.58 grams here, again, they said sufficient enough. So really, this is our limiting reactant. Okay, so we need to now change this to delta H, which is going to be in kilojoules per mole. Okay, well, what did this come from? This came from 0.158 grams of our magnesium. Okay, so we've got to change our grams of magnesium to moles of magnesium. Well, that's not too hard. 0.158 grams magnesium. There's 24.3 grams of magnesium and 1 mole of magnesium. Okay, so now we're going to take our joules, change them to kilojoules, Remember, all we have to do is divide by 1,000. Okay. And then we're going to divide our kilojoules by our moles. So our delta H value is a negative 4.6. Well, I apologize. I worked this problem before, but my handwriting is so bad I can't read it. 3.096 divided by 0.006502. 463 kilojoules per mole. Okay. And since I know that the heat went up, I know that is a negative value. Okay. Here's one for you to try. Pause the video, see how you do, and then check back with me. Now, this one's a little tricky because we're mixing two solutions. We've got 50 milliliters of silver nitrate, and we've got 50 milliliters of hydrochloric. Okay. So, when we're looking at our mass, both of those are going to be in the coffee cup. We get to assume that the solution is 1 gram per mil. Okay. So if that's the case, then for our Q, our mass is still going to be 100 grams. They tell us our specific heat capacity. Then we're going to take our 24.21 minus our 23.40. Okay, so we get 100 times 4.18 times parentheses 24.21 minus 23.40. Okay. Now, if this is the case, this is in joules. Remember, our grams cancel. That should have a Celsius. Sorry about that. And so we have that many joules. That comes from, we have to figure out how many moles. Now, this isn't a 1 to 1 to 1 to 1 ratio. That's delightful. Okay, so from here, if I have a 0.100 molar, okay, and I have 50 mils, 0.050 liters, how many moles is that? Well, fortunately, it's the same over here, so we're reacting the same number of moles. But if I check that, 0.1 times 0.05, that's equal to 0.005 moles of product or reactant, either one. Okay, because everything's in a 1-to-1 ratio. So I need to divide this by this and make sure that I have it in kilojoules. Well, to change this to kilojoules, I'm going to make that 0.33858 kilojoules. Divide that by 0.005 moles. I know that it's giving off heat, so it's going to be a negative delta H value. So somewhere around 68 kilojoules per mole. Hope that helps.